93 million miles away, two clouds of magnetized plasma are converging in the dark, one chasing the other down at speeds most spacecraft will never touch. And when the faster one finally catches the slower one, it will not simply pass through it. It will swallow it whole. Forecasters have a name for what happens next, and it is not a subtle one. They call it a cannibal coronal mass ejection, one solar eruption devouring another, merging into something larger, messier, and considerably harder to predict than either explosion would have been on its own. And when a storm like that finally reaches Earth, the number on the forecast sheet has a habit of being wrong in only one direction, too low. This is the story of how the sun builds a storm out of two storms, why the merger itself is the reason official forecasts keep underselling, what actually shows up, and what it would mean for the planet if the incoming cannibal turns out to be bigger than anyone currently expects. To understand why two explosions merging into one is so much more dangerous than either alone, you first have to understand what a coronal mass ejection actually is, because it is easy to confuse with the flash of light that usually gets the headlines. A solar flare is a burst of radiation, arriving at Earth at the speed of light in about 8 minutes. It can scramble radio communication on the sunlit side of the planet, but it does not by itself threaten satellites or power grids in a serious way. A coronal mass ejection is something else entirely. An actual physical cloud of solar material, billions of tons of magnetized plasma, torn free from the sun's outer atmosphere and hurled into space, where a flare is a flash, a CME is a cannonball, and cannonballs take time to arrive. Depending on their speed, they typically take somewhere between 1 and 4 days to cross the gap between the sun and the Earth. Under normal circumstances, that gives forecasters a useful window. A single CME launches, its speed and rough trajectory get measured from satellite imagery within hours, and a forecast model projects roughly when and how hard it will strike, along with an estimate of how disturbed Earth's magnetic field is likely to become as a result. Geomagnetic storms get ranked on a 5-step scale, G1 through G5, running from minor to extreme, and most single CME impacts land somewhere comfortably in the lower half of that scale. But the sun does not always fire once and stop. Active regions, the sprawling, tangled sunspot groups where this kind of eruption originates, often produce multiple flares and multiple CMEs within a span of hours or days, especially during the most turbulent stretches of the roughly 11-year solar cycle. And when two of those eruptions launch from the same general region in quick succession, something mechanically inevitable can happen. The second eruption, if it happens to be moving faster than the first, simply catches up to it. Picture two cars leaving the same driveway minutes apart, the second one driving considerably faster than the first. Given enough distance, the second car does not just arrive behind the first, it overtakes it entirely, and if the road were narrow enough, it would eventually merge with it, the two becoming a single or larger vehicle carrying the combined mass and momentum of both. That, in essence, is what a cannibal CME is. A faster eruption, launched after an earlier, slower one from the same or a nearby active region, physically catches up to its predecessor, somewhere in the space between the sun and the Earth, plows into it and absorbs it, merging two separate clouds of magnetized plasma into a single, denser, more tangled structure that then continues on toward whatever lies in its path. Solar physicists sometimes refer to the result as complex ejecta, a technical way of saying that what eventually reaches Earth is no longer a single, relatively coherent cloud with one dominant magnetic orientation, but a scrambled combination of two, their magnetic fields tangled together in ways that are extraordinarily difficult to model in advance. And that tangling is precisely why cannibal CMEs carry an outsized reputation among the people whose job is to forecast them. Here is the physics behind that reputation, and it comes down to a single number that matters more than almost anything else in space weather forecasting: the orientation of the incoming magnetic field, specifically whether it points north or south relative to Earth's own magnetic field as the cloud arrives. When an incoming CME's magnetic field points south, opposite to Earth's northward pointing field near the equator, the two fields can link up in a process called magnetic reconnection, essentially opening a temporary doorway that allows solar particles and energy to pour into Earth's magnetosphere far more efficiently than they otherwise would. A CME, with a strongly south-pointing field arriving fast, can turn a fairly modest amount of mass into a genuinely severe geomagnetic storm. The identical CME, arriving with a north-pointing field, instead can strike Earth just as hard physically and barely register as a storm at all, because the magnetic doorway simply never opens. For a single, uncomplicated CME, forecasters can often get a reasonable early read on that orientation by studying the magnetic structure of the sunspot region it erupted from and refining the estimate as the cloud crosses instruments stationed further out in space. For a cannibal CME, that job becomes dramatically harder. The merger scrambles the internal magnetic structure of both contributing clouds, twisting and compressing field lines that were originally oriented independently of one another into a single, chaotic structure whose net orientation is genuinely difficult to predict until the cloud is almost on top of the spacecraft doing the measuring, typically a satellite, stationed in roughly 1 million miles from Earth, which offers barely half an hour to an hour of advance warning once the merged cloud finally passes it. This is the mechanical reason official forecasts for Cannibal events tend to carry unusually wide error bars, and why space weather agencies routinely attach language to these forecasts that they do not use for ordinary single CME events. Phrases like, fair confidence in Earth arrival, but intensity remains highly uncertain due to the complex interaction between the merging ejecta. That is not forecaster caution for its own sake. It is an honest description of a system that is, by its nature, harder to see clearly until it has almost already arrived. There is real recent history behind that caution because Cannibal CMEs are not a hypothetical curiosity dreamed up by space weather agencies to hedge their forecasts. They have produced some of the most dramatic geomagnetic activity of the current solar cycle. In early June of this year, an unusually unstable sunspot region designated 42455, a rare type of sunspot known as anti-Hale, carrying a magnetic polarity reversed. From what theory says an active region in its position on the Sun should normally have, produced a rapid sequence of X-class flares alongside multiple coronal mass ejections within the space of about a day. One of those ejections, moving faster than the one launched just ahead of it, caught up to and absorbed its slower predecessor before either had traveled the full distance to Earth. NOAA's own space weather models flagged the merger explicitly, and when the combined Cannibal cloud finally arrived, it produced a strong, and by some measurements, possibly severe geomagnetic storm, the kind capable of pushing the Aurora borealis into the skies above more than 20 American states far from its usual polar range, an outcome noticeably stronger than what either individual eruption would likely have produced striking Earth alone. That anti-Hale instability turned out to matter twice over, because sunspots with reversed magnetic polarity are, for reasons still not completely understood, disproportionately prone to producing repeated, closely spaced eruptions in the first place, precisely the condition a Cannibal CME needs to form. Fewer than 1 in 10 sunspot groups display this reversed configuration, but when one does, forecasters know to watch it especially closely, both for the frequency of its flares and for the increased odds that any two of those eruptions might end up chasing each other down in space. None of this is unprecedented in the longer historical record either. Solar physicists studying archival data have identified Cannibal-style mergers behind several of the more memorable geomagnetic storms of the past few decades, cases where the eventual strength of the impact caught forecasters off guard precisely because two separate eruptions had quietly combined en route, well outside the range of Earth-based instruments, to observe the merger directly as it happened. In one especially striking historical case, a Cannibal-style eruption reportedly crossed the gap between the Sun and Earth in as little as 14 hours, dramatically faster than the 1 to 4 day window a typical single CME requires, and produced a geomagnetic disturbance strong enough to cause real problems for the technology of its era, so what actually happens on the ground, or more precisely to the technology surrounding the ground, when a storm like this arrives, stronger than forecast. The most visible effect, and the one most people genuinely enjoy, is the Aurora. A strong or severe geomagnetic storm can push the shimmering curtains of green, red, and violet light that normally stay confined near the poles dramatically further toward the equator, sometimes becoming visible across the northern half of the United States, much of the United Kingdom and continental Europe, and equivalent latitudes in the southern hemisphere. For skywatchers, an under-forecast Cannibal CME is often simply good news arriving with extra enthusiasm. But the same merged, tangled magnetic structure that makes for a spectacular light show also makes for a rougher ride for the infrastructure quietly running underneath it. Strong geomagnetic storms induce small electrical currents in anything long and conductive, high-voltage power transmission lines, cross-country pipelines, railway signaling equipment, currents that can strain transformers and occasionally trigger protective shutdowns if grid operators have not prepared adequately in advance. Satellites experience increased atmospheric drag as the upper atmosphere heats and swells in response to the storm, subtly nudging their orbits and complicating precise tracking, an effect that becomes more pronounced the stronger the storm runs. GPS accuracy can degrade, sometimes significantly, for hours at a stretch. High-frequency radio communication, still relied upon for some polar aviation routes and maritime operations, can experience real disruption on top of whatever blackout the initial flare already caused. None of this, even at the severe end of the scale, threatens the kind of society-wide catastrophe that occasionally makes its way into worst-case scenario headlines. That level of consequence remains the territory of truly extreme G5 class events, benchmarked against historical outliers like the 1859 Carrington event, which are measured perhaps once or twice a decade at the very most. But the specific danger a Cannibal CME poses is not that it produces some fundamentally new category of catastrophe. It is that it produces a normal, survivable category of storm at a strength nobody adequately prepared for, because the forecast available in the hours beforehand simply could not see the merger clearly enough to say so with confidence. That is precisely why space weather agencies keep emphasizing the same practical message every time a Cannibal event is flagged as a possibility. Grid operators in regions with any history of geomagnetic sensitivity are encouraged to review protective procedures and reserve capacity well before the cloud arrives, rather than waiting for a final confident number that a complex merger may never fully deliver in time. Satellite operators are encouraged to consider safe mode postures for sensitive instruments, and the public, for its part, is encouraged to treat the moderate to strong, possibly stronger language in these forecasts as an honest description of real uncertainty rather than forecaster indecision. Because in this particular corner of space weather, the single biggest source of surprise is not the sun's initial eruption. It is the second one, quietly gaining on the first, somewhere in the dark between here and there, until the moment the two finally become one. As the current merger continues its approach, that is the story worth watching closely over the coming hours. Not simply whether it arrives, which forecasters already consider fairly likely, but how strong it turns out to be once it's true. Merged magnetic structure is finally close enough to measure directly. Every Cannibal CME carries the same built-in irony. The very process that makes it dangerous, two storms becoming one, is also the process that keeps its true strength hidden until almost the last possible moment. Forecasters will keep refining the number as new data arrives, but history suggests the safest assumption, right up until the cloud is measured passing that final outpost 1,000,000 miles from home, is that the official forecast is a floor, not a ceiling. Understanding why that final measurement matters so much requires understanding just how thin the margin for advance warning actually is, even under the best circumstances. The instrument most forecasters lean on for that last critical read sits at a location in space called the first Lagrange point, roughly 1,000,000 miles sunward of Earth, a spot where the gravity of the Sun and Earth balance out enough for a spacecraft to hold a stable position relative to both. Satellites stationed there act as an early warning tripwire, sampling the actual speed, density, and magnetic orientation of an incoming CME as it physically passes by. For an ordinary CME traveling at a moderate clip, that tripwire buys perhaps 30 to 60 minutes of genuine advance notice before the same material reaches Earth. For a Cannibal CME moving faster because it now carries the combined momentum of two separate eruptions, that window can shrink even further. 30 to 60 minutes is enough time to issue an alert. It is not enough time to redesign a power grid's operating posture from scratch, reroute a fleet of polar flights already in the air, or meaningfully change a satellite's orbit, which is exactly why the agencies responsible for tracking these events spend so much energy on the days beforehand, rather than the hour of arrival itself, flagging active. Regions with a history of repeated eruptions, watching for the specific signatures that suggest two CMEs are on a collision course with each other before they ever reach that final tripwire, and pushing out graduated hedged forecasts precisely so that grid operators and satellite teams have some lead time to prepare for a range of outcomes, rather than a single confident number that a late-breaking merger could quietly invalidate. There is also a broader pattern worth noting, one that stretches beyond any single storm. Solar activity runs on an approximately 11-year cycle of rising and falling intensity, and multiple lines of evidence suggest the current cycle is at or near its peak, a period known as solar maximum. During solar maximum, active regions capable of producing rapid, repeated eruptions become measurably more common, which means the specific conditions required to build a Cannibal CME, two flares, close together in time, launched from a region prone to firing more than once, arise more often than they do during the quieter years of the cycle. That does not mean every eruption during this stretch will merge with another. Most will not. But it does mean forecasters are treating the possibility of a merger as a live consideration for essentially every major eruption right now, rather than a rare edge case worth mentioning only occasionally. None of this is cause for alarm on its own. It is, instead, the ordinary operating reality of living on a planet orbiting an active star during the loud part of its cycle, a reality space. Weather forecasters navigate the same way meteorologists navigate hurricane season, tracking developing systems, refining predictions as better data arrives, and being candid when real uncertainty remains. attached to a forecast rather than pretending a clean number exists when it does not. The sun does not owe anyone a tidy, predictable eruption. Sometimes it sends two. For anyone watching the sky over the coming nights, that uncertainty cuts in a genuinely favorable direction. A forecast that undershoots tends to undershoot toward more aurora, not less. A wider storm than expected generally means the shimmering curtains of light reach further from the poles than the official outlook promised, not that the display simply fails to appear. Photographers and sky watchers who have learned to read these advisories tend to treat the phrase moderate, possibly stronger, less as a warning to stay indoors and more as an invitation to find a dark horizon and wait. The same complexity that keeps grid operators and satellite teams cautious is, from a folding chair in a dark field far from city lights, simply the reason tonight's sky might turn out to be better than advertised. What ties all of this together, in the end, is a single unglamorous truth about forecasting anything built from more than one moving part. A single storm, born from a single eruption, is hard enough to predict with precision. Two storms, born minutes or hours apart from the same unstable patch of the sun's surface, chasing each other across 93 million miles of space, before finally colliding somewhere in the dark and becoming one. That is not simply twice as hard to forecast. It is a fundamentally different problem, one where the most important number, the final merged magnetic orientation, does not fully exist as a knowable quantity until the two ingredients have actually finished combining. Until that moment arrives, every forecast issued is necessarily a best estimate built on an object that has not yet finished becoming itself. And that, more than any single number on a 5-step scale, is the real reason a Cannibal solar storm is the one kind of space weather that keeps forecasters watching the data scroll by right up until the last possible minute.